Last presentation, we learned how scanf is using memory addresses to send particular values into particular locations in memory. This presentation will cover memory diagrams, which are a useful tool for understanding what programs are doing and how memory works. This presentation will follow Section 8 in your workbook, so please follow along as we go. Some of the topics we'll cover are a review of what scope is, different types of memory, and finally, activation records or memory diagrams. Memory diagrams are a very important part of this course, so I'm splitting this presentation over multiple presentations. Part 1 will cover the review of scope and the different types of memory. So to get us started, let's think about how much data or how many variables we can actually store in our computer's memory. Assuming our integers take 4 bytes and we can represent a birth date with a single integer, how many birth dates could we store in the computer's RAM if it has 2 gigabytes of RAM? This might be a bit of a trick question, and it even tricked whoever made the solution manual. It's tempting to enter 2 billion over 4 into your calculator and get 500 million birth dates could be stored in your memory. But because a computer's memory is based on a base 2 number system, 1 gigabyte is equal to 2 to the power 30. So 2 gigabytes is equal to 2 to the power 31, which can then be divided by 4 to get 536,870,912 birth dates that can be stored in 2 gigabytes of RAM. It is quite an impressive number. It's definitely a size of problem that we'd rather have computers deal with than have us deal with it ourselves. Before we begin defining the different types of memory available in a computer program, it will be useful for us to refresh our definition of scope. The scope of a variable can be thought of as the lifetime of a variable. It answers questions like when a variable appears and disappears. Understanding scope is fundamental to understanding how to draw a memory diagram. So let's refresh with an example. Here's an example of a C program which declares one function prototype, a void function named foo, which accepts one integer parameter. After that, there's one global variable defined. Global variables can be accessed from any line that follows the declaration of a global variable. You can see in the diagram that the box below the global variable outlines the scope of the global variable, which is the remainder of the program. As we continue down, as the compiler would do, going from top to bottom, the next variable that we encounter is called local. Local is a local variable. It's defined within the braces of the main function, which means that it can only be accessed from inside of main and after its declaration. This dashed box outlines the scope of local. After local is declared, there's another set of braces which creates a new level of scope. Inside this new level of scope, another variable called veryLocal is defined. VeryLocal can only be accessed from within the braces and after the declaration. This innermost box highlights the scope of veryLocal. Notice that all 3 variables, veryLocal, local, and global, can all be accessed in this innermost scope. However, once we move past the closing brace, veryLocal disappears, and it's no longer in scope. Local is, however, still in scope because it's within the braces of main and after the declaration. Function foo is in scope as well because it comes after its declaration, which is at the top of the file. The parameter of function foo, int x, is only accessible from within the scope of foo, which is enclosed by the braces surrounding the body of the function. This final dash box outlines the scope of the variable x. Now that we've reminded ourselves of what scope is in a program, we're ready to define the different types of memory that can be used by a program. There are three types of memory: static, automatic, and dynamic. As the name suggests, static memory is always accessible and never goes away. In the example that we saw, the variable global is in the static portion of memory. Automatic or stack are the variables that are declared inside of functions. We had a couple examples of automatic variables: local, very local, and the int x is also another automatic or stack allocated variable. The last type of memory is known as dynamic or heap memory. Dynamic memory in C can only be accessed through pointers, although pointers don't have to point to dynamic memory. We saw in the previous presentation that we declared a pointer which pointed to the address of a local variable. When you look at the memory space of a program, there are distinct sections for each of the three types of memory. This figure illustrates how the memory is laid out. At the top is the program code, which contains all the instructions that the program needs to execute. After that is the static memory, which never changes in size and doesn't need to grow, comparing that to the stack and the heap, which both need to grow as more functions get called and as more memory gets allocated. The stack and the heap are at the opposite ends of the program's memory to allow them to both expand into the large address space gap in the program's memory. You can think of that large address space gap as memory that hasn't been used, but is available for the program to access. Let's see more examples of how these different types of memory get allocated, beginning with static allocation. In the example in section 8.61, the variable x is declared outside of any function, which makes it a global variable. Global variables aren't the only ones that are allocated on the static portion of memory. For example, static int z explicitly requests to be on the static portion of memory. That means that static int z will survive for the lifetime of the program. Another type of data that gets allocated statically are string literals. And string literals are easy to identify because they're anything that's contained within a pair of quotation marks. Automatic or stack allocation will be the most familiar to you. But for most situations, automatic allocation is the way to go. Automatic allocation happens when you declare a local variable or a function argument. In the example, z, a, b, x are all automatically allocated on the stack. Dynamic allocation is memory that goes on the heap. In C++, there's special operators called new and delete for allocating dynamic memory. We'll see them in the second half of this course. In C, there's multiple choices for calling functions which can allocate memory on the heap. And that concludes part 1 of this multi-part presentation. In part 1, we reviewed the rules of scope, and we covered the different types of memory: static, dynamic, and automatic. In part 2, you'll learn how to draw activation records to describe the state of a program at any point in its execution.